ARP4761A and its companion 4754B were revised by S18 and Working Group 63 and published in December. These apply regardless of the chosen technologies and would work the same way for traditional or machine learning implementations. Most of the interactions will be through the system process of ARP4754B or ED-79. We'll refer to these existing guidelines and avoid repeating their content in ARP6983. Regardless of the technology used in the implementation, the safety assessment process has three major steps. The FHA asks, what if the function is lost or erroneous, to set safety objectives. The PSSA evaluates the architecture against those safety objectives, identifies safety requirements, and assigns development assurance levels. And the SSA evaluates the actual implementation against those safety objectives for certification. We are planning for the initial release of ARP6983 to cover ML items up to Level C. The assignment of an item development assurance level for the ML item would be determined at the system level in the PSSA. The IDAL assignment in the PSSA starts from the failure condition category from the FHA and may also take credit for mitigating features in the system architecture. The PSSA would also identify constraints or functional or performance requirements needed to support the claims made in the PSSA. ARP6983 would be used for assuring the ML-based item, while the existing ARPs would be used at the system level, including the integration of the ML-based item into the system. There may be a role for probabilistic performance factors of the ML item. This may be a partial benefit, but by itself is not enough to provide assurance. We are currently discussing the role of such factors in the committee now. This work is both rewarding and challenging. While we have hopes of completing the new ARP soon, we are still working through issues, so it may take a little longer. If you'd like to learn more, please contact either Working Group 114 or SAE G34.
My name is Darren Cofer. I'm a Principal Fellow and Research Scientist at Collins Aerospace. Machine learning-based systems, such as neural networks, present a number of verification challenges as we consider deploying them on board aircraft, potentially performing safety-critical functions. Some of the key assurance activities performed as part of traditional development processes, such as model and source code traceability and structural coverage metrics, do not provide confidence in the correct operation of an ML-based system, nor can they provide any indication that the system has been sufficiently tested to identify unintended behaviors. One of the technologies that may help address this challenge is formal methods. Formal methods, also called automated reasoning, is a subfield of computer science in which formal logic, discrete mathematics, and computer-checked proofs are used to analyze digital systems, both hardware and software. Formal methods tools based on mathematical proof allow us to go beyond what can be achieved with test-based verification alone. For example, we can check that the Pythagorean theorem holds for any specific triangle by testing it. However, if we want to know that the theorem holds for every right triangle, we need a proof. Similarly, when structural engineers build a bridge, they do not determine the adequacy of their design by driving heavier and heavier trucks over it. They rely upon mathematical tools like finite element analysis to identify the high-stress points in the design and check that the material properties of the structure provide sufficient strength. The use of formal methods is motivated by the expectation that, just as in other engineering disciplines, performing appropriate mathematical analyses can contribute to establishing the correctness and robustness of a computing system. In the aviation domain, the formal methods supplement to DO-178C, known as DO-333 or ED-218, provides guidance on the use of formal methods to satisfy software assurance objectives. Outside of aviation, formal methods are being used by big tech and cloud services companies to address functional and cybersecurity requirements that can't be handled by testing. Formal methods tools are now being developed for verification of neural networks. These tools provide the ability to prove functional and stability properties and can identify adversarial inputs that result in unintended behaviors. They can also be used to comprehensively analyze the entire system input space to bound the output behavior of the system, thus providing a characterization of the generalization capabilities over unseen data. For a thorough description of formal methods tools applied to machine learning systems in aviation, including a detailed use case, please check out the IPC project report produced by Collins and EASA titled Formula, Formal methods use for learning assurance.